Okay, we're going to go ahead and get started. Welcome to the first brown bag presentation of the fall. The first brown bag presentation with a live audience in too long. Welcome everyone back. For those who are new, welcome. This semester we'll have a lot of interesting, hopefully, presentations, and we'll be doing this kind of hybrid probably for the whole fall, where a certain number of people can come in and to the room itself. The presenters will typically be here, so it's a little bit more live for them, good practice for them. And other people can watch you online, and this also will be recorded, so these brown bags are being recorded so people can watch them later. We have two really interesting presentations today. I would say both presentations are in the area of propulsion and power, but from different kind of aspects. Our first presentation is by Rob Clark. Rob is an NSEG fellow. He's working on his PhD degree here at Georgia Tech, obviously. He got his BS from Purdue and his MS from Ohio State. He's got some interesting experience before coming here. He's also worked at GE. He was a Edison engineering program, development program there. He's worked on a number of engine and cycle analysis programs, and he's now working for Professor Mavris in ASDL in that same area. And I won't read your title. I'll let you do it. So thanks, and everyone please welcome Rob.
All right. My presentation today is on the design and analysis of an aircraft thermal management system linked to a low bypass ratio turbofan engine. This is really a repurposed presentation that I gave for a conference this past summer. I just want to acknowledge my co-authors, which is Ming-Chuan Chi, Jonathan Gladden, and Dr. Mavris in the ASDL. So I'll start out with just some motivation for this research. If you look at the graph on the top right, you can see power required in military aircraft versus time. And if you just kind of look over time, you can see a pretty distinct upwards trend in the amount of power that military aircraft require. And those large power requirements lead to large thermal loads that need to be dissipated in those aircraft. Even just, your most basic efficiency for an electronic component, if it requires a megawatt of power and it's at 95% efficient, then you have 50 kilowatts of power that needs to be dissipated as waste electrical heat. A couple different sources have provided some ranges for what thermal loads might be in future aircraft. And those range anywhere from 500 kilowatts to 15 megawatts, depending on the class of aircraft you're looking at. So there's a massive amount of heat that needs to be dissipated in military aircraft. Just to summarize what I just said, the thermal management systems on these aircraft are going to need to be able to handle megawatt class loads. That's a significant barrier for future military aircraft design. A little bit more background. The typical fuel sink or heat sinks that are used are either a ram air stream or the engine fuel. The engine fuel is typically kept at a pretty cold temperature on the aircraft. So as that engine fuel is pumped into the engines, you can actually use that as a heat sink. However, right now, the fuel is really at its max capacity in terms of heat sink. So you can't really just keep dumping more and more heat into the fuel as you add more waste heat to the aircraft. So we have to find more creative ways to get rid of that heat. One way that's done is using a ram air stream where you just have a scoop on the aircraft and it's a cold air stream that you can put heat exchangers in and get rid of heat that way. However, the advent of variable cycle engines, which actually have a lot of variable geometry to change the bypass ratio actively throughout the flight envelope, provide a different stream for cooling the engine. And then additionally, most aircraft, whether it's commercial or military, all use an environmental control system to cool cabin air. So, when you go in a traditional aircraft and you're flying somewhere, it's pretty cool in there. That's actually because air has been pumped through the engine to a high pressure, and then that pressurized air is cooled down in an environmental control system and then pumped into the cabin to provide pressurized cool air for you. And so we wanted to look at, can we use an ECS-style architecture but actually handle significant waste heat from military aircraft? There have been lots of studies all over the place. I've got a number of references if you're curious that you can look at, but most of those studies only ever look at just the environmental control system on itself. It doesn't really look at how that system performs when it's actually attached to an engine. So our goal was to actually look at how does an environmental control system type architecture behave when it's attached to a real engine but operating at much higher load. So we need to develop a high fidelity TMS model and then integrate that with a turbofan engine. Now I'm going to quickly walk through how NPSS models are developed. NPSS stands for Numerical Propulsion System Simulation. This is kind of the gold standard tool when you're doing any type of propulsion modeling in the aerospace industry. NPSS models are built from a series of base elements, things like compressors, burners, turbines, ducts. You connect those together, and then you, as the model designer, select specific variables that you want to be independently varied as you solve that model. And those are things like mass flow into the inlet of the engine or the shaft speeds. You usually have 2 or 3 shafts in an engine. And then the continuity and conservation laws that we're all familiar with, energy balances, mass balances, those are all enforced through the use of what's called a dependent variable. And a dependent variable has 2 equations, a left-hand side equation and a right-hand side equation. A simple one is perhaps shaft torque. You have torque going into a shaft from a turbine. You have torque coming out of the shaft from a compressor. And so you need to balance the speed on that shaft so that the left-hand side and the right-hand side are equal. In other words, you don't have a certain amount of torque coming in and a different amount of torque coming out. And so the way NPSS works is it has a solver, which is a modified Newton-Raphson solver. If you've taken a different numerical methods class, you should be familiar with those techniques. It varies all the independent variables that you set up until you actually have a converged solution where all the dependent left-hand side and right-hand sides are equal or within some tolerance. However, as the model designer, you have to be very careful because you can come to a numerically converged solution that is not actually physically or thermodynamically possible. So it might tell you that your shaft needs to be running at 1,000,000 RPM, but if you just look at that solution, you clearly know that's not a physical solution. So you have to be very careful when interrogating and setting up these models. With that, there's 2 different phases in an NPSS model design. You have a design phase where you actually size the turbomachinery components in the case of an engine. And you actually have maps that tell you how, say, a compressor works in terms of flow, pressure ratio, and efficiency. So you actually set your design point on that map, and then you move to the off-design phase where then you vary performance. So if I change my airflow into the engine, now my compressor needs to adjust to a new operating condition. And so your maps are how that happens. But you start out in the design phase where you physically size the engine, and then you move to an off-design phase where you see how that engine that has now been sized performs in different conditions. On the 2 tables on the bottom of this chart, I just have typical independent and dependent parameters that are used in a model. So in the design phase, you might vary your turbine pressure ratios in order to meet the torque on all of your shafts. You might vary your burner fuel flow in order to meet your target temperature that you want, et cetera. And then when you're in off design, now you're going to vary fuel flow so that your nozzle has the right flow going through it. Sorry, you're going to vary inlet flow so your nozzle has the right flow going through it. Now, instead of varying turbine pressure ratios to match your shaft torques, you'll actually vary the shaft speed. So these are just a sample of typical dependents that are used. Now, how that works is we started by building what we're calling a companion engine model. And in this case, we really tried to roughly model an F-35 class engine. So the F-135 is Pratt & Whitney's engine that's on the F-35. We were not trying to match performance of the engine exactly, but we wanted to create a rough model of a low bypass ratio turbofan. So on the right, you can see the design parameters that we use. We just used a single design point, which is sea level static. And you can see the different parameters we tried to match, 28,000 pounds of dry thrust, an overall pressure ratio of about 30, a turbine inlet temperature of 3,600 degrees Rankine, a bypass ratio right around unity, so a very low bypass ratio engine. And then the tip pressure ratio for the fan is 5, and the hub pressure ratio for the fan is 3. One thing to clarify, though, is this engine was not intended to be a high-fidelity model of an engine. The goal of this research was actually just to model how the TMS performs when attached to an engine. So we didn't need the engine to have perfect performance, but it's at least going to provide, ballpark performance for how the boundary conditions that TMS might see. Now I'm going to walk into the actual thermal management system architecture that we developed for this study. This is a pretty busy chart, so don't worry if you can't follow along, but I'm going to try to walk through all the different components on here. At the top, we can see the actual engine, a very rough block diagram of the engine where you have a fan, a compressor, your combustor, and then your turbine. And from that engine, you have bleed ports from the high-pressure compressor. So those bleed ports are where you actually can take air out of the engine, and that air will actually be used as working air, that's what we call it, in this air cycle system. So that working air passes through a primary heat exchanger in a ram air stream. So this whole, all the little arrows here represent actual flow streams. So the bleed air goes through a heat exchanger, and that heat exchanger is really cooling down the air. It's hot, high pressure air coming from the engine compressor, and so you have a cold ram air stream that's cooling it down in your primary heat exchanger. And then we actually go through another compressor and we compress that air because it's been cooled, so we have more margin to compress it to a hotter temperature. So we get it to higher pressure, higher temperature, and then we send it back through another heat exchanger in that ram air stream. So now we have a relatively high pressure source of air, but at a relatively low temperature, which is exactly what we want. The rest of the fan or the ram air stream just has a fan behind those two heat exchangers to make sure you can always pull air through. So in situations where you might be on the ground and you don't have a lot of inlet recovery from high-speed air moving into that inlet, you need to have some motive force to move the air through. So we have a fan that's situated behind that. And that fan, as you'll see later, is connected with the shaft to all the other turbomachinery in the air cycle system. So once the air has come out of that secondary heat exchanger, we have relatively low temperature but high pressure air. It then passes through a water extraction loop. This is just another series of heat exchangers that try to get that air down to a low enough temperature that you can actually extract any moisture in it. The air will eventually get to a very, very cold sub-freezing temperature, and any air or any water that's in the air would freeze into ice crystals on your turbomachinery, and that would be very damaging to those. So we try to actually separate out all the air. You're trying to get it below the dew point of that air. From there, we move into the two turbines. So you have cold air now that's at a high pressure but low temperature, and it's expanding out through turbines. So now you're actually going to get it to an extremely low temperature. And the net result is that by the time we come to what's called the thermal transport bus, you actually have an extremely low temperature and low pressure source of air. And the idea there is now that we have a extremely low temperature source that's a heat sink for all of the heat load that's coming off of the engine. So this TTB loop actually takes our heat load from the aircraft, it passes it through a loop of fluid, and then there's a heat exchanger, what we call the TTB heat exchanger, where now the very cold ACS working air is serving as a heat sink for the thermal conduction fluid that's actually just transferring heat from the aircraft into our system. So that, I think I have an extra box here. That's just what's happening in the last stage here. Once the working air comes out of that heat exchanger, it's actually just dumped overboard. You don't try to get any additional thrust out of it. You just have a low temperature it's been heated up from all the aircraft waste heat, and then it's dumped overboard as off the aircraft. Now, we did two studies here, one where we actually used a ram air stream and another where we said, let's not add any additional hardware and space to the aircraft. Let's instead try to use the bypass of the engine. So the primary and secondary heat exchangers that were previously in a ram air stream have now been placed into the bypass duct of the engine. Now all the components associated with that ram air stream don't exist, and instead the bleed air from the engine goes into the primary heat exchanger that's now situated in the bypass duct. The difference there is that that bypass air has been heated up in the fan. So the fan has a 3 to 5 pressure ratio at its design point. So whenever you raise the pressure of air, you're also raising the temperature. So now we have a much warmer sink of air. So you'll see later that that significantly degrades performance of the system. So then how do we actually model this? I'm going to go back to the same schematic and I'll walk through. As I mentioned before, this fan needs to provide enough pressure ratio to actually pull air through. That's equivalent to saying that the nozzle at the back of this stream needs to have a pressure ratio greater than 1, which is what's actually pulling air through that system. So that's the first thing, is that the fan needs to provide enough of a pressure rise to always move air through there. The pressure coming out of the TTB heat exchanger needs to be greater than ambient static pressure. And that's another way of saying air needs to actually be able to get out of the system. So if in these two turbines we expanded the air so much that now its static pressure was below ambient, then if you tried to eject that air, the atmospheric pressure would actually just push air back into the system. So that's just a physical requirement, is that we can't ever go below ambient static pressure at the exit. In addition, the last pressure requirement is that you can't compress the air so much in our compressor here that you actually exceed material capability. So you have to limit the pressure rise in that compressor so that you don't exceed material temperature limits. Now, as I mentioned before, we're trying to condense any extra water out. So at the water separator, you need to actually have a low enough temperature in the working air so that water will condense out and you can extract all of that water. Furthermore, in the TTB or thermal transport bus loop, you have some type of, it could be fluid, it could be air, but if it's air, you don't have a limit. But if it's some type of heat transfer fluid, you have a minimum temperature that fluid is designed to operate at. So the coldest point that that fluid will ever get is at station T1 there in the corner, which is right after it's pulled, it's dumped its heat into the ACS working air. So that station T1 has to be limited. It can't go below a certain temperature. And that temperature is somewhat arbitrary, but if you look at any type of thermal transport fluid, in our case, we use something called Dow Siltherm 800. It actually does have a minimum operating temperature, so that becomes a limit for the cycle. And then the last primary temperature limit is that when we pull heat in from the aircraft system, and this model, we don't know anything about the aircraft. We don't know what fluid is in the aircraft's own internal heat transfer system. We know nothing. All we know is that there's going to be some temperature. And just, the basic laws of heat transfer say if you want to pull temperature, you have to go from hot to cold. So we have some arbitrary upper limit on the temperature of the heat transfer fluid as well. And we have to remain below that limit so that we can actually pull heat out of the aircraft. Then in off design, this is, I think, mislabeled. In off design, you'll actually bypass this fan if you don't need any pressurized. So my design point, actually this is for off design or design. If my design point is in the air traveling at say Mach 8, you're going to have a lot of inlet recovery coming into this whole ram air stream. And if that's the case, you actually want to bypass that fan because the fan is really just a parasitic power coming off of the whole system. So if you don't need to provide any pressurized, you can just simply bypass the fan. The last important thing to note is we have these bypass valves around the turbines. In a perfect world, all the working air in the system would go through each of those turbines. The turbines, I have 5 minutes. Those turbines would fully expand that air, and you would get as much work out of it as possible. With the idea is that work goes into your compressor to get as high of a pressure as possible, so then you can further expand it. However, the temperature limits all around the system actually require you to bypass a lot of that air around these turbines, so you can't actually get as much work out of it as you would like. And that's an irrelevant comment for this presentation. I'm going to skip. So the last thing here, what we've talked about is all sorts of pressure and temperature limits, but we haven't talked about how do I actually figure out how much flow I need. The way you do that is you can do a very basic heat exchanger analysis, where if you have a counterflow heat exchanger model, you can look at the capacity rates. I'll let people work through the math on this if they want. Basically, the cold side of a heat exchanger has to be the driving side because that's the side that's pulling heat out from one side to another. So the amount of flow on the cold side really determines how much heat you can get out of that heat exchanger. So we can actually determine ratios of flow throughout the system by looking at all the heat exchangers, and then the final amount of flow that we need to size the whole system based on the actual amount of heat you're trying to get from the aircraft. I'm going to skip this because we sort of already went through these and we're running out of time. Let's look at some results of how the system actually behaves. So we looked at a couple different design points for the system. On the right chart, you can see a rough envelope for a typical aircraft where you have your Mach number on your x-axis and your altitude on your y-axis. Typically, you have what's called the upper right-hand corner, which is your fastest speed and your highest altitude. In this case, we didn't look at supersonic conditions, so we just looked at a typical cruise condition at about 35,000 feet, Mach 0.8. And as well, we looked at a sea level static condition. So we designed these systems, both the ram air-cooled system and the bypass air-cooled system, at both of these points to try to capture the corners of that envelope. So we'll look quickly. This chart looks maybe a little small from here, but this is a TS diagram that's actually showing all the stations. So you look on the chart here, station 1 is the very inlet to that first heat exchanger in the ram air stream. That's the top point here. This is just a TS diagram walking through all the different points in that system. The key here is that in these two large segments, 1 to 2 and 3 to 4, this is where you're actually rejecting heat from the system into your cooling stream, whether it's your ram air stream or your bypass stream. And then at the very bottom, 13 to 14, this is where you're absorbing heat in from your aircraft. So what we see here is this is actually the same system, our ram air-cooled system designed at sea level static for two wildly different loads, a 50 BTU per second and a 5 BTU per second, so an order of magnitude difference. But you actually can't see a difference in the cycles here. So what's happening is because the temperatures are fixed, the cycle actually works itself out so that regardless of the load, the cycle stays the same. And the only difference is the amount of flow that you need to handle that load. If we look at changing the design condition from sea level static, which is the boxes and X's, to a cruise condition. So if we instead design the system at cruise, you see a totally different cycle, but what you'll notice is that the temperatures across that heat exchanger at the very end of the system actually remain fixed, because those are design temperatures. We're trying to maximize the heat we can get out of the system, so we're operating at our limits. So it makes sense that those temperatures would stay the same. And so although we have a different overall cycle, the key thing is that those temperatures remain the same. This is, instead of designing the ram air-cooled system, we have a bypass air-cooled system. And the key to note here is that when you have a bypass air-cooled system and you design it, the diamonds here are designing it at sea level static conditions, you actually can't reach the temperatures you need. So you can't actually operate at a sea level static condition because that bypass air is just too hot. You can't force enough heat into it. So you actually just can't reject any heat at all. And so that system really doesn't work. And the last one we'll look at is if I design both of those cooling systems at cruise conditions, you actually end up with an identical cycle at the key component, which is that heat exchanger in the TTB loop. We can skip this. These are irrelevant, but what I will cover is this last slide. So the key of this whole system is the thermal transport bus loop here, where we have the aircraft load coming in, and then the cold air from the air cycle system that's taking that heat out of that load. If you recall, I said that future aircraft systems need to handle megawatt class loads, and so for several different variations of design, you can see what is the max capability we were able to dissipate. If we design the system with a ram air-cooled system at cruise, you can only get around a kilowatt of energy off the aircraft, whereas at sea level static, you can get about a quarter of a megawatt, so about 250 kilowatts. So that's significantly different capability depending on where you design the system, but that's still nowhere near a megawatt of dissipation. And where those numbers actually ultimately come from are the temperature limits that we impose on this loop. So for this case, we had a minus 40 degrees Celsius limit, minus 40 degrees Celsius and Fahrenheit. That's a crossover point on those two scales. But that was actually the limit of Dow Siltherm 800. So we couldn't go any colder. And we arbitrarily said a point just above freezing is what the aircraft system will be giving us heat at. But then what we tried to look at is what happens if we vary the delta in temperature there? How much more heat can we actually dissipate? And what we did is we actually did it in two different ways. So we decreased the lower limit, so from, say, minus 40 degrees Celsius to minus 60 degrees Celsius. And conversely, we also increased the upper limit. So instead of 1 degree Celsius, 10 degrees Celsius. So there's two different ways you can increase the delta across that loop. And what you see is that the squares here represent decreasing the lower limit, and the triangles represent increasing the upper temperature limit, where the X's are your baseline. And the system actually would prefer to go colder. So if you lower that lower limit as much as you can, that's what will actually expand your temperature dissipation capability. But unfortunately, that lower limit is the one where you actually have a material limit. If if your heat transfer fluid simply can't go that cold and still operate, that will limit the system. So actually improving the capability of the system to handle megawatt class loads really solely depends on how much flow you can bleed off the engine and what the temperature difference is that you can get across that loop. So just some quick conclusions. The colder temperatures in a ram air-cooled stream actually enabled a wide range of design points. In the bypass stream, you simply can't even operate at sea level static conditions because the air is too hot after being compressed by the fan. We ran a case where we actually oversized the bypass aired system, and it was able to achieve very similar performance, but at the cost of much more engine bleed. And so the results, if we were to have looked a little bit closer into them, would have showed that the ram air-cooled system appeared to be better, but that system has a lot of drawbacks when you actually integrate it on an aircraft. It's a lot of extra weight and volume that you have to put on an aircraft to have a whole extra ram air stream. It also increases the size of the radar cross-section, which for a military aircraft is extremely important if you're trying to evade detection. And then, as I said, adding a ram air stream into an aircraft that maybe has a fixed outer mold line may not be possible because you just don't have volume inside the aircraft. However, as I mentioned before, variable cycle engines provide a good way to combine a cool stream of air without actually having to add in a ram air. So the future work is primarily actually designing a variable cycle engine model and then looking at full level mission analysis. Instead of just a couple design points, how can we actually look at the performance of the system across a whole range of a mission and see how can we optimize mission performance with these systems. That is it. If you want to look at any of the references, they're all here. And if you ask me, there is a whole paper on this that you can read a little bit more. Thank you very much.
We have time for some questions. If you have a question, I will. Anyone in the room will ask a question.
You mentioned that weight was a concern. Can you talk about the weights of different systems you're considering?
Sure. So let's go back up here. This slide is ugly to in presenter mode. So the difference in weight between the two systems primarily comes from the actual ram air stream, where you have an extra inlet, you have a diffuser, you have a whole extra piece of turbo machinery, which is a fan, and then you have a nozzle. You still are going to have these two primary and secondary heat exchangers. Those are going to be on the system whether or not they're in the bypass stream or the ram air stream. So the weight really comes down to primarily the weight of that extra turbo machinery component plus the volume. And so in terms of actual what is the delta weight difference, it really depends on the scale of the system and how much flow you have. I mean, a compressor is going to weigh hundreds of pounds probably with the amount of air this is. So you're looking at, you know, hundreds of pounds of difference, which for an aircraft that might have a max takeoff weight of 15,000 pounds, that adds up to, you know, several percent. So that ends up, you know, spiraling you in your design for that aircraft.
On that line, so typically in heat exchangers, you can move a certain amount of heat depending on how much mass flow rate you're going to have on the two sides and how much air you have. So were you constraining the mass flows in some way in this process that you didn't explore other options?
So what we were doing, let me see if I can get to the right one. What we did is we said we have to have some motive force in this loop to push that coolant fluid. And we said we want to minimize, and what's not shown in the schematic is there's going to be some pump that's moving your heat transfer fluid. We said we want to minimize the amount of work that pump has to do, which means we want to minimize the total flow rate in that loop. So because the cold side has to be the driving force in terms of capacity rates, you want your cold side to be the limiting capacity rate. What we did is we actually fixed the ratio of capacity between those two sides. That's certainly not the only way you could analyze this, but just in terms of writing some way to ratio those flows, we said we want to minimize hot side flow, but our cold side needs to be the minimum heat capacity. So we said our hot side heat capacity be just above.
But did you vary how much air and power you're drawing from the engine? That's basically the thing. Did you limit that?
Okay, so yes, engine bleed air was limited to 10%. So it couldn't ever go above 10% of core airflow or W25 in the engine. So we did limit that. And then we varied the amount of heat load coming from the aircraft. And so what that did in the design point is the heat load ultimately set the amount of air. And so when we figured out what the maximum heat capacity of the system was, it was with the engine running at its maximum bleed air. All the temperature limits were maxed out. And then you were just determining how much heat can you actually then transfer through that heat exchanger. Did that answer your question?
Okay, so.
You're talking about parallel engine cycles, right? That PG is talking about that, like three-stream rapid engine cycles. So, what's the difference between the bypass and the upstream?
So with let's go. This is the best we've got here. So the difference between a typical bypass, like a separate flow or a mixed flow, is that your variable stream has a much lower pressure ratio in front of it. So the fan here, actually in a variable stream engine, that fan gets split into multiple stages. And the bypass stream, there's really three streams. You have a third stream, your normal bypass stream, and then your core stream. That third stream still sees some amount of compression from the first stage of that fan. And then the core sees a lot more compression. So kind of three levels of pressure. You have a low pressure third stream, a medium pressure bypass stream, and then your typical core stream. So the advantage that gives you is because you have much lower pressure rise in that third stream, you have a lot lower temperature rise as well. And so you still have a relatively cool source of air. And typically you have a lot more freedom as well to vary how much flow is going through that third stream. Because typically you actually reintroduce that third stream into the bypass stream after the turbines, but before the nozzles of the engine. So you have a lot more design freedom with how that engine works, and you can depending on how you design the engine, you get a lot of cold air, a high volume of cold air in that third stream, which is really what the system relies on, having that cool sink to power the whole system.
If you can get enough heat exchanger area to fit in.
Yeah.
Okay, well, let's thank our speaker again. Switch over. So our second speaker is Chris Douglas. Chris is proof he can graduate. He recently graduated and finished his PhD working for Professor Lewin. He is on his way to go to the Ecole Polytechnique and Technical University of München on a Marie Curie fellowship. And so he's looking forward to that, I think, a lot. But he's basically going to talk about things that he was doing as part of his PhD here at Georgia Tech.
That's right. Hey, everyone. Glad to be here. It's my first talk in person since November 2019, so good to be back. I'm going to be talking about the dynamics of landward swirling jets. And this is a talk that I could motivate a lot of different ways. There's a ton of different applications of swirling jets, which are a pretty fundamental flow. We have swirling flows which exist in hurricanes, in supernova, even in your aorta and in other parts of your body. And then obviously swirling jets have an application in engineering where they're used in gas turbines, like in this image here. They're also used in things, everything from like a Dyson vacuum cleaner to a separator in a concrete plant. They're basically all over the place. And so today I'm going to be talking from a power propulsion sector type perspective and motivating it this way. So this is an example of, these are both examples of swirling jets, so I'm going to be focusing on the bottom one here. So why do we use swirling jets in injection systems and combustors? The main reason is because they enhance mixing and entrainment. Basically, one of the problems in a combustor is to mix your fuel, is to have the combustion take place in a relatively small space, something like an airplane. You're relatively constrained by space, and you want that combustion to happen in a compact way. You want the flame to be compact so that it's very stable, so that it reinforces itself, and you want to minimize impingement of that flame on things that can melt, like all the walls around the flame. And so swirling jets are a good way to do that for some reasons that I'll talk about in a second. So gas turbines are something that are on the rise recently, not just in aviation applications, but also in ground power. As we transition away from coal and nuclear, one of the things which is really helping renewables grow are these natural gas power plants, which are probably not a long-term solution, but are something that can solve a lot of the intermittency issues that currently face a lot of clean renewable technologies. And so gas turbines have grown to be an enormous share of the U.S.'s primary power generation. That's also true worldwide. And it's also expected to continue to grow over the next couple decades. And so in the interest of minimizing the climate impacts of gas turbines, it's really important to understand these kind of fundamental issues really well, so that we can kind of squeeze every ounce of power with the minimum amount of impact. And one of the key reasons why we're concerned about impact is not necessarily climate, but is human health. And if you looked at a gas turbine system in the 1960s or around earlier than 2000 for sure, you would probably see a lot of non-premixed combustion systems. And what that means is that you're operating in a regime, actually I'll use the mouse here. You're operating in a regime which is right near the stoichiometric condition. And basically what that means is that you operate on a part of the curve which is two things. First of all, it's very high temperature. We're looking at a fuel air ratio flame temperature diagram here. So your operating temperature is very high, which means that the flame is very good at stabilizing itself. It also means that there's a relatively small change in flame temperature for a change in equivalence ratio. So basically, if you have a fluctuation in your system, things get a little weird. That you don't really need to worry. It's just going to get, it's not going to have a strong impact on flame temperature. But in this new paradigm of lean premix technology, which is necessary because burning a non-premix flame, you operate at very high temperatures, you generate a lot of NOx, which is extremely toxic, or is extremely detrimental for human health. In order to get lower NOx, you have to get to lower temperatures. And the lean premix technology is a way to do that. You basically use more air and less fuel, and by doing so, you tend to you burn at a lower temperature, and you generate a lot less NOx. And so that puts you at this point here on this diagram. And you can see a couple things are different here. First of all, we're at a lower temperature, which is what we wanted to get less NOx. But a side effect of that is that, first of all, we're very close to this lean limit, which if we cross that, we have the flame extinguishes, at least locally, and that can have some unforeseen detrimental effects. And also, we're at a part of the curve with slope, and that means that fluctuations have sort of a knock-on effect, where a small fluctuation leads to another fluctuation in temperature, and that basically means that you're operating at a point where things are much more uncertain. You're much more sensitive to fuel-air fluctuations in a lean premix condition. And combustion instability is kind of the key motivator that I'm going to use for this talk. So basically, combustion instability is what happens when you have some fluctuation in heat release. That heat release fluctuation introduces a change in the acoustic field. You know, if you have a rapid heat expansion generating an acoustic wave, that acoustic wave bounces all around inside your combustor and excites some flow disturbance. That flow disturbance then can come back and interact with the flame again to create another heat release disturbance. And if, as you go around this loop, you have you're energetically positive, then bam, you've got a combustion instability. It's going to continue to grow and reinforce itself until basically it saturates, which could be just a loud noise that you hear from your engine, or it could be something really bad where you see really, really strong fluctuations, crazy dynamics happening in your engine, and this is basically something that you can't operate. You can't safely do that. Bad things happen. These are some examples of gas turbine engines that have gone, that have experienced strong combustion instabilities. And so this top example is actually a picture of the combustor. But another problem is that a combustor is right upstream of a turbine, which is very fragile blades. And if you're not controlling the temperature, which is going of the fuel of the fluid, which is going into that turbine, then you can really damage your turbine blades and not just your combustor. And if you imagine you break off one of these blades in the turbine, that thing's spinning really fast, and it just spreads all the way down through the rest of the turbine. So it's really bad when that happens. So just to summarize that motivation, there's a really clear reason why we need swirling jets to work in modern gas turbine combustors. They're increasingly susceptible to all these things. And since they do rely on swirling jets, we really need to understand this hydrodynamic coupling mechanism in order to understand how to build better engines and how to build better gas turbines. And since one of the key limiters here is this the sort of hydrodynamic coupling mechanism, that sort of piece of the puzzle, we really need to have a strong understanding of swirling jet dynamics. Swirling jets are complicated fluid flows, which we don't know a lot about, which I'll talk about in a second. So the objective of the work, which kind of motivated my thesis, and which I'm going to be talking about today, is kind of what dynamics underlie the natural behaviors of these fluid systems. So if we think of sort of the simplest model we can of a swirling jet, I'm just going to pick a top hat profile, which is what you'd think of as probably a jet type fluid. You can imagine an orifice to the left of this. And so I'm showing kind of two different components of the velocity profile here. We've got what you would think of as the jet, and we've also got this blue curve, which is showing the azimuthal velocity component. So basically, there's a twist which is happening as this comes, as this kind of blows out as a jet. It's also rotating. And jets that have, or fluid flows that have a structure like this I'm just going to call them swirling jets. They're subject to three fundamental instability mechanisms, which we do know very well. The confusing part is how they interact. So the first is the centrifugal mechanism. And this is a common thing which has been well studied in things like a Taylor's wet flow. So this is the flow between two rotating cylinders. We get centrifugal instabilities, which manifest Taylor rolls. We also have the Kelvin-Helmholtz mechanism, which happens anytime you have a shear layer. Basically, you get this vortex roll-up, which happens along your shear layers. And we sort of classically think about that in sort of a 2D planar sense. But in a swirling jet, there's both an axial and an azimuthal component. And so this shear has kind of two sort of cardinal directions, which again makes things more complicated than these sort of nice, clean cases we have in the examples below. And the last thing is the Coriolis mechanism, which is something that happens because, just like the centrifugal mechanism we're talking about, something that's rotating, the things that rotate are subject to the centrifugal force, to the Coriolis force, as well as the centrifugal force. And basically what this does to fluid flows is this kind of weird phenomenon called inertial waves. And it's hard to concretely pin down one thing which is manifested by inertial waves, but one good example in swirling jets is the phenomenon of vortex breakdown, which is something I'll talk a little bit about later. So now that was kind of sort of an ideal example. Now I want to talk about some experiments and show what swirling jets really do, not just in these ideal situations. So I'm going to be using this number here that I'm calling S. This is the swirl ratio. Basically, these people, Liang and Maxworthy, did an experiment where they had a rotating pipe with a honeycomb. So basically, you can just imagine you're shoving flow down a pipe, got a honeycomb in it, so as the pipe rotates, the flow rotates, you have a swirling jet. And they look at it using a bunch of cameras and a laser diagnostic system in this test tank. Starting with S equals 0, you can see this is sort of what your intuition would probably be like if you study jets. This is what a jet flow sort of canonically looks like if it's not swirling at S equals 0. We just have axisymmetric jet. We have nice axisymmetric vortex rollup due to Kelvin-Helmholtz instability, and sort of that develops until we get turbulence further downstream. As we start to increase swirl, things start to change a little bit. So at very low swirl, we see a slight break in symmetry. And that's sort of the first key that something weird is going on that's not in a regular jet. You can see that those sort of nice axisymmetric vortex rings are now getting tilted. We're transitioning to turbulence much earlier than we were before. And as we continue to increase swirl, we continue to see this breakup happen. We get stronger helical waves, and that turbulent region sort of keeps moving closer and closer to the nozzle. And then at the highest swirl ratios, at least the highest swirl ratios considered by this study, we get vortex breakdown, where this is greatly zoomed in on the nozzle here. And you can see that we have a fully turbulent region, which is basically recirculating fluid. So the jet now has this aerodynamic blockage. And this is actually one of the key reasons why swirling jets are used in combustion systems, is because if you have reverse flow like this, and you can imagine there's sort of a flame in front of this, you have a bunch of hot products which are recirculating to contact your cold unburned fluid. So you have a very stable, you have an aerodynamically stabilized flame rather than requiring metal right there, which can melt. Downside of that, of course, is that you have fluid, which is not solid, so it can move around and you can have a lot of dynamics. And I'll talk a little bit more about vortex breakdown in a second. But before I do, I just want to talk about the symmetry breaking phenomenon. So like I said, swirling jets undergo the symmetry breaking thing at sort of low swirls before vortex breakdown. And what that tends to look like are these sort of helical or double helical instabilities, like the one you see here. So this is done basically in this identical experiment almost. And you can see this sort of S-shaped instability, which sort of develops. These are different cross sections of the flow as it develops, and you can see this nice S-shaped thing appear. And one thing I'm going to use in this talk is the azimuthal wave number M to sort of quantify what the shape, or to describe the shape of these instabilities. So M equals 2 basically means that as you walk around the central axis, you see 2 peaks and 2 valleys. Two peaks and 2 valleys. Sorry, using myself here. And then for M equals 1, you'd see 1 peak and 1 valley. So basically, an M equals 1 has an appearance that looks kind of like this, whereas M equals 2 has an appearance that looks kind of like this. In swirling jets, we tend to see M equals 1 and M equals 2 instabilities. And there's been some evidence from earlier studies that shows that these instabilities manifest from what are called supercritical instabilities, or supercritical bifurcations. And basically what that means is that as you increase your swirl number, you're gradually approaching a condition where an instability can appear, and as you continue to increase it, it sort of it grows linearly, or its amplitude grows as the square of the departure from a criticality condition. So basically, if you don't have hysteresis, if you increase your swirl, you're going to get an instability. If you decrease your swirl, that instability is going to go away. And so this is some experimental evidence that has been widely cited for this, to explain this, and kind of sort of explain these as supercritical bifurcations. However, I'm going to present some work which shows that this actually isn't the case, that it's actually a subcritical bifurcation in some cases, which can lead to a very different understanding of some of these physics. Now, I told you I was going to come back to vortex breakdown, so let me just quickly address something here. So vortex breakdown has a few different shapes. You can see in figure A here that there's sort of a time average sense. This is an instantaneous picture, but you can kind of put your time average hat on maybe and kind of understand that there's sort of a a recirculation feature which is happening here, which is persisting for some time, enough to make it a time average feature. And that as we change the swirl number, once vortex breakdown occurs, we can see different types of vortex breakdown. We can go from a bubble like this, sort of a small thing where the flow kind of goes around this aerodynamic blockage and then sort of continues in the bulk downstream direction. Or we can see what's called a cone shape, where the flow is just sort of ejected laterally almost, and it doesn't seem to come back, at least not at any close distance from the jet. And so very different flow topologies leads to very different plane behavior. It's very important to understand when are we going to be in one regime versus the other, thinking in terms of I want to design a combustion system. So the overall picture, which I want to paint of swirling jets, is that it's really simple. That it's just a battle between dissipation and vortex stretching. And even this very simple picture is something that's not very well understood. Once we go into reacting swirling jets, we throw in a ton of different physics, which we don't understand. So really, I mean, just the fact that we still have a lot of work to do to understand this is a testament to how much more fundamental work needs to be done in the types of flows we're doing using for engineering systems. So just to briefly summarize what I just threw a lot of at you, we've got these co-rotating and counter-rotating structures, which emerge from bifurcations, which I'm going to just show evidence from the literature that say they're supercritical. I'm going to contest that in a little bit. And then there's this phenomenon of vortex breakdown, which is really important for stabilizing flames and leads to bistability between bubble states and cone states, which I kind of talked about a little bit. So the way I'm going to analyze this problem is using bifurcation analysis, which is a numerical technique. I'm going to be studying a jet configuration, which is super, super simple. We just have, it's very similar to what I showed in those experiments. We basically have a rotating pipe. So we get a fully developed laminar flow coming in from a long pipe. I'm sorry, I shouldn't walk away, so I stay in the camera here. Okay. It injects into a large open domain with just a static containing wall and just sort of does what a swirling jet does in there, and I'm going to study what it does. To do this, I'm going to use a non-react. I'm just looking at non-reacting stuff for this talk. Constant density Navier-Stokes, which I write this way. I'm not going to spend too much time here, other than to say we can describe this flow by two parameters, Reynolds number and the swirl number, and that's it. And we can look for a bunch of different states, thinking in terms of dynamical systems. If you've taken dynamics and bifurcations class, you'd recognize any system that was written like this. You understand that a system like this has steady states. It might have periodic states. And so that's kind of the perspective I'm going to take at analyzing this. I'll skip over approach here. So now to show some results. What I've got here is a bifurcation diagram. And what this shows is how the minimum of the axial velocity along the center line evolves as a function of the swirl ratio. That's what this top figure shows. And then below that, I've got the growth rate, the linear growth rate, which basically shows if there's an instability in the flow, which tells you whether a given saddle, which is just represented by a line in this diagram, whether it's an attractor or whether it's a repeller, basically. Oops. Oh, I went all the way back. Sorry about that. So let's take a journey where we start at 0.1 and move to 0.9. And as we're doing that, basically, we're changing the swirl number, not necessarily increasing it, changing. So as we go from 0.1 to 0.2 to 0.3, we can see that we're just increasing. All that's happening is swirls increasing. We can see that the jet is spreading a little bit faster. We get more viscous entrainment. But nothing absurd is happening. It still looks largely like a jet. This is the quasi-columnar jet theme. As we go from, as we hit 0.4, we can see that we have a vortex breakdown recirculation bubble appear. And 0.4 is a critical point. It's an instability where a saddle node bifurcation occurs, and we step onto an unstable manifold, which is indicated by this light gray line. There we can see we transition from having a bubble type breakdown to a cone type breakdown. Afterwards, we experience another saddle node bifurcation, and then we can continue to increase swirl off as high as we want, and we see that we transitioned into a wall jet regime. So this is just sort of a film that goes along the combustor, or the wall in this case, not a combustor. And so the main conclusion from this is that we have bistability. That means that solutions are multi-valued in this little gray band right here. And that's really important because it means that you could spontaneously jump from having one type of solution to another and back, and things like combustion-driven noise could cause this. And so there's actually been some work done in Tim's group that's shown an example of this, which I don't have time to talk about. And we can do this again, this sort of same analysis that I just did for swirl number and Reynolds number. And basically, the main idea that I want to show is that we can approach this problem from a dynamical systems perspective and understand all of the transitions that we saw in those experiments earlier. We can see this bistability here. We can see these are bifurcation neutral curves associated with different bifurcations. So we can see m=2 bifurcations or m=1 bifurcations. Basically, that by analyzing this problem from a dynamical systems perspective, even though we're stuck in the laminar case because turbulence is difficult to model, we're able to understand all the fundamental physics which are happening for laminar swirling jets. Before I finish, I just want to quickly show, I mentioned an anecdote about how some experiments had shown that the m=2 instability appears in a supercritical manner. And this is some evidence that shows that they don't necessarily appear in a supercritical manner. There are at least some situations where they do appear in a subcritical way. And again, in the dynamical systems world, subcritical has a meaning which basically says that you can form hysteresis loops where as you change a parameter, you spontaneously jump from one type of solution to another rather than smoothly transitioning like you would in a linear system. And so the main point here is I just wanted to say that there's m=2 and m=1 instabilities. The m=1 instability, at least in this case, always occurs or tends to occur by a supercritical bifurcation, and that manifests an instability which looks like this. I don't have a video to show you, but I have a paper which I'll cite at the end if you're more interested, which has some videos. And then the m=2 instability, which I also showed some pictures of in the beginning. That one does occur by a subcritical bifurcation, at least for these parameter values. And that's different than what has been seen earlier in the literature. As you go to higher Reynolds numbers, you can get a lot more complicated. You can see a lot of different types of instabilities which occur, which I studied in that paper, but I don't have time to talk about that here. So I just put a few pictures because they look kind of cool. And I guess with that, I'll end it so that I have time for questions. If you want to check out some of this work in more detail, this is an article which I wrote earlier this year with Ben and my advisor, Tim. And then these are some summary points to sort of help guide discussion. Thank you.
Okay, welcome for questions. You'll have to twist your head around that. I'll start one off. You talked a lot about the swirling flows, and you hinted at the potential combustion issues with aerodynamics. Could you say what you think the most important implications on combustion swirling flows do you think you felt doing?
Yeah, so here's an example that I skipped over to save time, but now I'll go back to it since you asked. So I also have done some of these similar calculations for reacting flows. And what I'm showing here are some visualizations of the flame surface. These are high Zeldovich number of about 10 premixed flames. And what it's showing basically is that this bistability, which happens as vortex breakdown occurs, can transition you from having a sort of a cone-type, almost Bunsen flame. As the flame propagates through that vortex breakdown bubble, you have a bifurcation to an M-shaped flame. And so you can imagine if you're not able to control your swirl to a very fine degree, or if you're changing different combustion parameters, you can change where that flame would sit. And if it bounced back and forth across that recirculation bubble, you'd have an enormous oscillation, potentially.
So you could have a heat release rate oscillation, you could have a pressure oscillation, you could have a heat load on the surface change. Yeah. Which would all affect the combustion lifetime. Right. Pressure rises, disruption.
Exactly. Yeah.
Other questions? Anyone online? Go ahead.
What's the swirl number for a cone shape?
So swirl number, I'm using a swirl ratio, which is just a ratio of the pipe's rotation rate to the average mass flux, to the average velocity coming through the pipe. And so that's the lowest swirl number that can happen here is at 0.6, which is about 2. But that persists to much higher states. Basically, one of the main results from this work is that the cone breakdown is no different than this wall jet. It's just that when you study an experiment, you have to put it in a container of some sort, and it sort of attaches to the wall of that container well before it attaches to the wall of the dump plane. So that basically those are the same thing. This cone breakdown and the wall jet are all the same type of solution. But the real bifurcation which happens, the hysteresis which happens, is not whether a vortex breakdown bubble exists or does not. It's whether that closes or whether it opens and attaches to the wall through the Coin effect.
Do you think the swirl number is sufficient to define when that happens, or is there other?
If you fix your other conditions, certainly.
Which ones do you think are important besides swirl?
The Reynolds number is certainly important. If you go to the high Reynolds number limit, it probably becomes less important. But at least for laminar flows, it's certainly an important quantity. Obviously, if you have expansions happening, like due to heat release, your heat release would be important because expansion is going to change the size of that bubble.
What about the expansion ratio of the device?
Yeah, geometric factors would certainly be something as well. Also, I should mention, this is all with a circular cross-section annular jet. Most combustion systems tend to use an annular type injector. And so you can think of, if I push the flow through an annulus instead of a circle, I'm going to be concentrating all that momentum further radially out. That means it's going to get more azimuthal momentum, so that'll change your swirl number as well too.
Anything else? Well, let's thank both our speakers.